Jupiter didn't smash the probe, it dissolved it. On December 7, 1995, the Galileo spacecraft released a 339-kilogram capsule into the atmosphere of the gas giant. A titanium hull, a heat shield as thick as a palm, a parachute system. The probe didn't crash into a surface, because there isn't one. It descended deeper and deeper, sending data for 57 minutes, then went silent. What happened next, engineers pieced together through simulations. Rising pressure and temperature tore the structure apart at the molecular level. Not shards, not fragments. Individual atoms dissolved into an endless ocean of hydrogen. 339 kilograms of engineering brilliance, reduced to nothing you could still call an object. And here's the puzzle. The very planet that destroyed the titanium probe looks like a watercolor postcard in every other internet image. Pastel swirls, marble-like patterns, gentle color fades. Where did this picture come from, and what lies behind it? Those mesmerizing images flooding social media with millions of shares come from the JunoCam, a camera mounted on the Juno spacecraft. Here's the first surprise. JunoCam isn't the mission's main scientific instrument. They put the camera on board to engage the public, to capture stunning visuals. The real heavy hitters are Juno's magnetometers and particle detectors, instruments that study the invisible forces around Jupiter. But it gets even more fascinating. The raw photos from JunoCam look nothing like the polished shots you see online. Volunteers from around the world, everyday people skilled in digital image processing, download the unprocessed data. They boost contrast, pull out colors, and sharpen details. The final images feel more like digital paintings than straightforward photographs. These enhanced versions shape our vision of Jupiter as something beautiful, almost welcoming. See those delicate swirls in the images? Those are storms. Winds there consistently blow around 270 miles per hour. To put that in perspective, the most destructive Category 5 hurricane on Earth starts at just 155 miles per hour. Each of those marble patterns is actually a vortex the size of a continent. On the enhanced photo, it only looks like a design on a cappuccino. Meanwhile, take a close look at how space agencies describe this environment in public. In NASA press releases, you'll find phrases like challenging environment and harsh radiation. It sounds serious, but manageable, like a tough neighborhood or a strict deadline. Yet in scientific papers, those same words carry a much heavier meaning. Harsh radiation means an unprotected person would die within minutes, not hours, minutes. And extreme conditions mean no known material can survive contact with the planet's interior. Remember this tactic: soft words masking unimaginable realities. We'll see it again. Here's another persistent myth. Jupiter is often called our cosmic shield, a giant protector that catches asteroids and comets with its gravity, stopping them from reaching Earth. It sounds logical. Massive size, powerful pull, therefore, it intercepts all the dangerous objects heading our way. But the scientific evidence tells a different story. The NICE model and the Grand Tack hypothesis, two leading orbital models of planetary migration, paint a more complicated picture. Yes, Jupiter's gravity deflects some objects away from the inner solar system, but it also funnels others straight toward us, specifically toward the orbital paths of Earth and Mars. Jupiter isn't a shield. It's more like an intersection where some travelers turn back, while others get pushed forward. And the final balance? It's still up for debate. Stunning images, carefully crafted by volunteers. Gentle descriptions, masks that hide a deadly truth. A dependable protector, a myth with a hidden catch. And if even the planet's outward appearance turns out to be an illusion, then what fuels the chaos lurking beneath those clouds we so painstakingly shaded in soft pastel hues? The oldest storm in the solar system never really started, and it will never end. It simply exists. The Great Red Spot has been under constant telescopic watch for at least 190 years. When Napoleon lost at Waterloo, this vortex was already swirling. When the Wright brothers flew the first airplane, it was still spinning. When Apollo landed on the moon, the storm was there. And here's the key point. in 1979, the Voyager 1 spacecraft confirmed what astronomers had debated for over a century. Storms on Jupiter, including the Great Red Spot, aren't just weather. They are permanent features. Not cyclones that form and fade away, but stable structures woven into the very fabric of the planet's atmosphere, like a mountain range made of gas. This range stretches about 2 Earth diameters side by side. If you could hold our planet in your hand and place it on the spot's surface, it would sink in like a coin dropped into a bowl of soup, and there would still be room for a second one right next to it. Stop thinking of the Great Red Spot as just a weather event. It's a geographical feature, steady like the Himalayas, only much older. But then, what keeps it moving? On Earth, storms feed off sunlight. The sun heats the ocean evaporates water. Water forms clouds, and the wind twists those clouds into storms. Without the sun, everything goes quiet. Jupiter plays by a different set of rules. This planet radiates 1.5 to 2 times more energy than it receives from the sun. In fact, it gives off far more heat into space than the sun ever supplied. The source of this excess energy is the leftover heat from the planet's formation 4.5 billion years ago. When gas and dust from the primordial cloud collided under gravity, their immense kinetic energy turned into heat. That heat hasn't faded away. Jupiter is cooling, slowly measured in cosmic time, and this gradual cooling drives its weather from within. It's not sunlight powering those storms. Instead, they're fueled by the planet's own internal furnace, running without any fuel. Just the momentum of its birth. Let's pause for a moment. Earth is a world warmed by its star. Remove the sun, and within weeks, the average surface temperature would plunge below -200 degrees. Oceans would freeze solid. The atmosphere would settle into frost. Jupiter, in the same scenario, would barely notice a difference. Its heat engine runs from within. It doesn't burn because something outside is warming it. It burns because it hasn't cooled down since the solar system formed. This is a fundamentally different kind of thermodynamics, something completely alien. Now let's go deeper. Far below the clouds, beneath the storms, pressure starts to twist matter in ways impossible on Earth. At Jupiter's core, temperatures soar to about 20,000 degrees Celsius. That's hotter than the sun's surface, hotter than the roughly 5,500 degrees that make our star shine yellow-white. The gas giant's core is hotter than the visible layer of the very star it orbits. The pressure reaches 45 million bars. At sea level on Earth, pressure measures just 1 bar. That's the force the atmosphere exerts on every square centimeter of your skin right now. In Jupiter's core, that same patch faces a load 45 million times greater. Imagine placing 20 Eiffel Towers stacked on a single postage stamp, and even that is a rough estimate. Under such immense pressure, hydrogen, the lightest, simplest element in the universe, stops behaving like a gas. It doesn't even act like a liquid in the way we know it. Electrons break free from protons and begin to move freely, like they do in metals. Hydrogen transforms into a metallic state. It shines. It conducts electricity. It behaves like molten silver, yet it's made entirely of just one element, atomic number 1. Here's the sobering truth. Metallic hydrogen doesn't naturally exist anywhere else in the solar system. On Earth, scientists have managed to create it only for fractions of a second, trapping a tiny sample between diamond anvils under pressures of several million atmospheres. Just fractions of a second. But deep inside Jupiter, this ocean flows continuously, for billions of years, thousands of kilometers thick. An ocean of liquid metal, once ordinary gas, transformed by pressure rewriting the rules of its existence. This churning metallic layer doesn't just sit quietly below the surface. It spins along with the planet. And this rotation gives rise to something invisible, yet far more dangerous than the crushing pressure that created it. Jupiter's spinning ocean of metallic hydrogen acts like a planet-sized dynamo. Electric currents swirl through this conducting fluid, driven by Jupiter's rapid 10-hour rotation, generating a magnetic field 20,000 times stronger than Earth's. But sheer strength isn't the most intimidating part. What's truly staggering is the scale of what this power creates. Jupiter's magnetosphere stretches 7 million kilometers toward the Sun. That's about 18 times the distance from Earth to the Moon, and that's just the sunward edge. On the opposite side, the magnetic field extends in a tail nearly 1 billion kilometers long, reaching all the way to Saturn's orbit. It's the largest structure in the solar system after the Sun's own heliosphere. Not a planet, not a ring, not a cloud of gas, a magnetic field. Here's what truly puts Jupiter's scale into perspective. If its magnetosphere glowed in visible light, it would look larger than the full moon to the naked eye from Earth. Night after night, the sky would hold this swollen ghost, bigger than the familiar lunar disk. But this isn't light. It's a trap. Jupiter's magnetic field grabs charged particles from the solar wind and accelerates them to nearly the speed of light. These particles build up in radiation belts, and here, physics crosses into biology. Near Io's orbit, radiation levels soar to doses hundreds of times higher than what would kill a human. Every hour. Not every year. Not every month. Just 60 minutes. But Io lies within Jupiter's inner radiation belt, and no one plans to send a mission there. What's far more intriguing and far more terrifying is the environment near Europa. That icy moon, beneath whose frozen surface there may be a hidden ocean of liquid water. The very moon humanity dreams of exploring. Around Europa's orbit, the background radiation dose reaches about 5.4 sieverts per day. That number needs some perspective. A sudden dose of 4 sieverts kills roughly half of those exposed, even with full medical support, IV fluids, blood transfusions, and bone marrow transplants. Half of the people die. Near Europa, those 4 sieverts accumulate in less than a day, and the next day, you get hit with just as much again. Numbers alone don't really hit home until you put them next to something familiar. An astronaut who spends 6 months aboard the International Space Station accumulates between 150 and 200 millisieverts over their entire career. That's their lifetime limit. Around Europa's orbit, that limit is reached before lunch on the very first day. The cleanup workers at Chernobyl, the ones who physically removed graphite blocks from the roof of Reactor 4, received about 250 millisieverts on average. A person wearing a standard spacesuit near Europa would absorb the same dose in under an hour. Simply put, the most irradiated people in Earth's history, firefighters, cleanup crews, victims of nuclear tests, received over a lifetime what Jupiter's radiation belts deliver in a single morning. This isn't about long-term risks, like an increased chance of cancer 20 years down the road. High doses of radiation trigger immediate, acute effects. Cognitive decline can happen within days. A person stops thinking clearly. Cataracts develop in weeks. The lens of the eye clouds over. Damage to the central nervous system and cancer don't wait until after the mission. They can start during it. The body begins to break down faster than the crew could complete their first scientific task. Radiation doesn't distinguish between living cells and microchips. Charged particles pierce through living tissue, and they do the same to silicon chips. They knock atoms out of the crystal lattice, flip bits in memory, and burn out transistors. Even radiation-hardened electronics, the kind that spend years in testing before heading to interplanetary probes, degrade within months inside Jupiter's radiation belts. Onboard cameras go blind. Sensors start spitting out noise instead of real data. Navigation systems lose their accuracy. Every extra orbit around the planet isn't just another dose for a potential crew. It's a ticking clock for every microchip on board. This invisible wall isn't made of stone or steel. It has no surface you can touch or lean against. Yet it kills, relentlessly, at the cellular level. equally indifferent to protein and silicon. The first thought that comes to mind sounds deceptively simple. Just build stronger armor, a thicker wall, a heavier shield. But this is exactly where the math starts working against us. Imagine engineers sitting down with their blueprints. The tasks sound straightforward. Calculate the wall thickness needed to reduce radiation to a safe level. But the very first formula shatters the whole plan. Radiation shielding doesn't work like a brick wall, where each new layer adds the same strength. Instead, the relationship is exponential. To cut the radiation dose in half, you don't just need twice as much material, you need a shield that weighs many times more. Cut it in half again? That demands another huge jump. And the next step? Each increase in safety costs more than the one before. Not just a little more, but an avalanche of extra mass and expense. Here's what turns a tough problem into an impossible one. The heavier the shield, the heavier the ship. The heavier the ship, the more fuel it needs to accelerate. More fuel means more mass, and that mass needs protection too. So the shield gets even thicker. That makes the ship heavier still, which demands even more fuel. Engineers call this the design spiral. Each turn spins the mass higher, and the equation never balances. Not because the materials are weak, not because the technology isn't ready, because the math won't budge. It's like trying to bail water out of a leaking boat with a bucket that has a hole in it. The bigger the bucket, the bigger the hole. Let's imagine, purely hypothetically, that someone actually built this ship. They hauled it all the way to Jupiter's orbit. They burned between 9 and 15 kilometers per second of delta V just to escape low Earth orbit and arrive there. Now, they have to return. Jupiter's escape velocity is 59.5 kilometers per second. For comparison, Earth's escape velocity is just 11.2. That's more than 5 times greater. Breaking free from this planet's gravity well demands propulsion technology based on physical principles humanity simply doesn't have. Not just unavailable yet, but completely unknown at the fundamental physics level. We don't even know what principle such engines would follow. 2 barriers stand in the way: radiation that forbids life, and gravity that forbids escape. And now, a third one. What does a person do when trapped? They call for help, press a button, send a signal, wait for a response. Radio waves travel at the speed of light. Nothing in the universe moves faster. But the distance between Earth and Jupiter is so vast that even light takes its time. A signal takes anywhere from 33 to 50 minutes to reach Jupiter, depending on where the planets are in their orbits. Round trip, that's between 66 and 100 minutes, at least an hour and a half. The crew presses the emergency button. 40 minutes later, the signal reaches Earth. The flight controller hears the cry for help, quickly crafts a response, and sends it back. Another 40 minutes pass on the return trip. That adds up to 80 minutes between "we have a problem" and "we hear you." By then, the crew has either solved the issue on their own, or no one is left to fix it. There's no real-time control, no guidance from Earth, no telemedicine. The crew orbiting Jupiter are completely cut off from civilization. Their voices reach home, but the reply comes too late to matter. Silence stretching for an hour and a half. Every day, every night, throughout the entire mission. The shield's mass grows faster than engineers can add fuel. Gravity holds tighter than any existing engine can push back. And light, the fastest thing in the universe, is too slow to carry a distress call in time. Everyone who's ever crunched these numbers arrived at the same conclusion. 9 spacecraft reached this planet in 50 years. None of them were built to come back. Pioneer 10, Pioneer 11, Voyager 1 and Voyager 2, Ulysses, Galileo, Cassini, New Horizons, Juno. Over 5 decades, 9 missions, 9 spacecraft. And here's what they all have in common. None returned samples. None carried a crew. None were designed for a return trip. This wasn't a coincidence or a budget cut. It was a verdict written into the mission plan before launch. When they sent Juno in August 2011, the paperwork already had its end date, a controlled descent from orbit, burning up in Jupiter's atmosphere. The final step of the scientific program was to destroy the spacecraft. Its titanium vault, shielding electronics from radiation, was never meant to be an escape pod. It bought precious time, delayed the inevitable failure of instruments long enough to gather the data. Then, ashes in the hydrogen clouds. Here's what's striking. Every new decade of observations revealed an environment far harsher than the last model predicted. The pioneers in the 1970s faced radiation they hadn't anticipated. The Voyager missions refined that picture, and it was worse. Galileo confirmed it, even worse. Juno measured it, significantly worse. 50 years, each new instrument, every flyby, and reality kept outdoing the worst-case scenarios. July 1994. Comet Shoemaker-Levy 9 is closing in on Jupiter. It hasn't touched the atmosphere yet, still flying through empty space, but the planet's tidal forces have already torn it apart into 21 fragments. From a distance, without any direct contact. Gravity at Jupiter's cloud tops measures 24.79 meters per second squared. That's 2.5 times stronger than Earth's gravity. Imagine every object in a room suddenly weighing 2.5 times more. The chair, the cup, your own body. The comet weighed billions of tons, and that wasn't enough to save it. That's why the upcoming missions take a different approach. The Europa Clipper, launched on October 14, 2024, will reach Jupiter's system around April 2030. It will perform about 49 flybys of Europa. It won't settle into a permanent orbit. Rather, it will fly by, gather data, pull away, then come back for another pass. 49 quick encounters instead of one long embrace. Because staying in orbit too long means radiation will destroy the spacecraft before the science mission can finish. This isn't a matter of engineering choice, it's a necessity. The European Space Agency's JUICE mission, which launched in April 2023, will arrive in July 2031 and follow the same strategy. Dive in, grab what you need, and back away. We've adapted to the hostility, not by conquering it, but by learning to dodge it. Now, let's talk scale. As of the year 2026, the catalog of known exoplanets is dominated by gas giants and so-called hot Jupiters. Sure, part of this reflects a detection bias. Larger planets are simply easier to spot, but that doesn't tell the whole story. Jupiter's mass, 318 times that of Earth, actually comes closer to the average planetary mass across the galaxy than our own home planet does. Jupiter isn't an outlier. It's not some cosmic monster lurking at the edge of the solar system. It's the norm, a typical example of what the universe churns out by the trillions. Earth, with its thin atmosphere, liquid water, and gravity just right for standing without being crushed, is the exception, a statistical anomaly, a fragile accident set against a galaxy filled with gas giants that shred comets from afar and incinerate probes on schedule. 2 spacecraft are currently on their way to this system. One will arrive in the year 30, the other in 31. Both were built following the exact same instructions in the final part of their mission plans. The same instructions that guided Juno. The same that directed Galileo. The very same that everyone who flies thereafter will follow. A one-way ticket.